The lives of the stars. One of the most fantastic claims in the whole of science is that we have good models to describe what goes on inside stars, how they are born, how they live, and how they die. Stars appear to us as no more than points of light on the sky at distances so enormous that light takes hundreds or even thousands of years to travel from them to us. Even the fact that we know the distances to the stars accurately is an achievement that would have amazed astronomers less than 2000 years ago. Although atoms and subatomic particles are, in a sense, just as remote from everyday experience because we cannot see them with our own eyes, at least they exist in laboratories down here on Earth and can directly be studied as the various models are tested in experiments. There is no way to test our models of stars by carrying out experiments on such distant objects. Even if we could, we might not live to see the outcome of those experiments, not because they would be dangerous, but because old age would catch up with us first. Those stellar models tell us that in many cases stars live for billions of years. A human lifespan is usually less than 100 years, and the lifetime of our entire civilization is less than 100 human lifetimes, less than 10,000 years. How can anyone seriously claim to know how a star was born billions of years ago and how it will end its life billions of years hence? In fact, the models that describe stellar structure and evolution are among the greatest triumphs of modern science and have been tested to high accuracy. They involve a combination of observation of the stars themselves using the techniques of spectroscopy, computer simulation of what goes on inside stars based on the system known laws of physics, and even actual experiments carried out here on Earth to test aspects of the models, notably the rate at which certain nuclear reactions go under conditions corresponding to those predicted to exist at the heart of a star by rival models. The whole package hangs together scientifically, but the key ingredient, the one without which astronomy would be no more than a kind of cosmic bean counting, is spectroscopy. As we mentioned in chapter 2, spectroscopy enables astrophysicists to identify different chemical elements present at the surface of a star by analyzing the light from that star. It even enabled Norman Lockyer to identify a previously unknown element, helium, from its spectral signature in sunlight. The distribution of starlight among photons with different energies, different colors in a light from a star also tells us the temperature at the surface. Using the famous black body energy curve, which was so important in setting Max Planck on the Earth to quantum physics, if you know the temperature at the surface of a star and its mass, then the basic laws of physics, the relationship between properties such as the temperature and pressure of a gas, and the computer models tell you how hot the star must be inside, what the pressure and density must be, and so on. We shall explain how we know the masses of stars shortly. And if you know the temperature and pressure at the heart of a star, and you know what the star is made of, then you know what nuclear reactions are going on inside the star. Experiments in laboratories on Earth then will tell you how much energy those reactions ought to be producing. This can be compared with the amount of energy a star actually does or radiate into space, and the models can be tweaked to make theory and observation agree more closely with one another. It all fits together beautifully and uses an enormous amount of physics, ranging from things so standard that no physicist really thinks about much about them, such as the temperature pressure relationship, to the most sophisticated nuclear physics experiment. The success of astrophysics is in many ways the culmination of the scientific ways of doing things, confirming that all of the bits of physics that were discovered separately really do work in the way that our models suggest when they are all put together. And all of this is mostly seen, of course, for the nearest star, the Sun. The birth of astrophysics can be dated precisely to a talk given in 1920 by the pioneering astrophysicist Arthur Eddington at the annual meeting of the British Association for the Advancement of Science, held that year in August in Cardiff. Until the beginning of the 20th century, it has been a major puzzle for astronomers to explain where the sun got its energy from. Geological evidence and Darwin's theory of evolution by natural selection required a very long history for the earth and by implication for the sun, but no known form of chemical energy such as burning coal could explain how the sun could have stayed hot for long enough for geology and evolution to do their work. The discovery of radioactivity involving energy released from the nuclei of atoms began to change the picture, and Albert Einstein identified the atoms Albert Einstein quantified the enormity of that change with its famous equation, which tells us that matter itself can be converted into energy, but at first people were reluctant to accept the full implication of these new ideas. It was one thing to use the idea of subatomic, that is, nuclear reactions, to explain why a piece of radium felt warm to the touch, but an enormous leap of faith to accept that same kind of process might explain the vast outpouring of energy from the sun, equivalent, according to Einstein's equation, to converting 5 million tons of matter into pure energy every second. For a time, people clung to a 20th century idea that a star like the sun might keep hot for long enough to explain events on Earth simply by shrinking very closely under its own weight, turning gravitational potential energy into heat as it did so. But even that could only keep it shining for few tens of millions of years. It was Eddington who finally squashed this idea and put astrophysics on the right track, telling his colleagues in Cardiff that only the inertia of traditions keep the contraction hypothesis alive, or rather not alive, but an unburied corpse. But if we decide to inter the corpse, let us freely recognize the position in which we are left. A star is drawing on some vast reservoir of energy by means unknown to us. Its reservoir can scarcely be other than subatomic energy, which it is known exists abundantly in all matter. We sometimes dream that man will one day learn to release it and use it for his service. The store is nigh inexhaustible. If only it could be tapped, there is sufficient to do the sun to maintain its output of heat for 1.5 billion years.